Hello, what we're going to look at today are similar solids. So the idea here is you have two three-dimensional solid figures, and if you have that their corresponding lengths are in a particular ratio, we're going to ask ourselves what effect does that have on surface areas or just corresponding areas and volumes. We'll also look at some problem solving related to this, and actually we'll just look at least one example of, well, what if I don't change them all by the same factor? But to start off, let's take a look at this example right here. I have two rectangular prisms, and you can see the length, width, and height of the first one are 9, 3, and 5 units. Of the second one, I have 18, 6, and 10 units. Now you probably notice immediately that there's something I've done with these numbers. These two rectangular prisms are similar. I can tell that they are similar. There's a scale factor of 1 to 2 because each of the lengths in this second figure are twice as long as the first figure. Alright, so the question then becomes, alright, if I do something like this, if I multiply each of the dimensions by 2, how many times as large are the surface area and volume of this larger prism compared to the smaller prism? Now, if I ask you this, in all likelihood, what most people are going to think, they'll say, oh, if I multiply all of the length, width, and height by 2, then that will double the area and it will double the volume. Well, think about that for a second. You can pause this or think about it for a second. Calculate the actual surface area of these two prisms. Calculate the volumes of these two prisms. Like I said, the natural thing is to think that if I multiply all the dimensions by 2, then what I'm going to do is double the surface area and the volume. Well, I have right here the actual calculations. The surface area of the first figure, 2 length width plus 2 length height plus 2 width height. If I go ahead and do that, what that's going to give me is 174 square units. For the second figure, what I see is I get 696 square units. Now those numbers are not by any means obvious, but 174 to 696, you can check that 696 is 4 times as large as 174. Right? Now what if I do this with the volumes? For the volumes, I can put in 9 times 3 times 5 and 18 times 6 times 10, and then what will I see? Well, the volume of the first solid is 135 cubic units. The volume of the second solid is 1,080 cubic units. Now again, these numbers aren't particularly obvious, but you can check. 1,080 is 8 times as large as the original, as the volume of the original prism that I started with. All right. So the question is, what is this telling us? Can I generalize this at all? And the answer is yes, I can, and that's in fact what we're going to do. We're going to do that so that we can problem solve some more interesting examples where I don't give you all the measurements or anything like that. So what we saw was I multiplied all of the original dimensions by 2. So the lengths were multiplied by 2, the surface area then was multiplied by 4, and the volume was multiplied by 8. Now hopefully you start to see the connection between those numbers, 2, 4, and 8. Now, before I explain generally what is happening here, what I'm going to do is an example where I actually work this out abstractly. All right. Sorry, my paper's a little bit out of order right here. The radius and height of a cylinder are both multiplied by 3 to create a new cylinder. We want to ask ourselves, how does this change the volume and surface area? All right, so I'm going to sketch a little cylinder just to help myself think about it. And you could do something like what I just did, come up with some numbers and try and figure out how that, affects this. But in general, it's going to make more sense, it's going to be easier to see if I do this abstractly. So what I said I was going to do was I was going to take the radius and I was going to take the height and multiply each one by 3. So the radius will be replaced with 3 times the radius, the height will be replaced with 3 times the height. All right, so we're asked, how does this affect the volume and the surface area? I'm going to start with the volume first because it's an easier calculation. The volume of a cylinder is pi r squared times the height. All right? So this new cylinder I've created, instead of the original radius, instead of the original height, those will each be multiplied by 3. So let's substitute and see how that changes this result. Pardon. There, I've substituted 3r for r. There, I've substituted 3h for h. Well, if I square this, 3r squared is 9r squared times 3h. Now I can clean this up. The easiest thing to do, what I want to do, 9 times 3 is 27. Then I have pi and r squared and h. Well, looking at those two, that should be pretty easy to spot. If I've got pi r squared h and I've got 27 pi r squared h, the new volume is 27 times as large. What about surface area? Well, the surface area of a cylinder is 2 pi r squared for the two circular bases at top and bottom, plus the lateral area, 2 pi r h, which is the circumference times the height of the cylinder, which what that is if you imagine unfolding, like if this was, say, a label around a soda can or something like that. If I unrolled that, this would be a rectangular region, 2 pi r long with a height of h. All right, so this is the surface area. Now again, I'm going to do exactly what I just did, replace r with 3r, replace h with 3h, and see how this actually affects the answer. So again, 3r squared is 9r squared. And if I multiply these two together, 3r times 3h is 9rh. Now I can go ahead and multiply this together if I'd like. Although at this point you can hopefully see what factor we have introduced to each of these terms. So I went from the original formula gives me 2 pi r squared plus 2 pi r h. Now I have 18 pi r squared plus 18 pi r h. All right. Well, how do I go from 2 to 18 in both of these cases? Well, in each case, I multiplied by 9, which actually, if you look at this next line up, you can see that in each of these statements, a 9 was what was introduced. Okay? So, going from 2 to 18, in either case, means I have multiplied this whole expression by 9. So the surface area is 9 times as large. Now think about that. In both of these instances, what did I do? I created two similar solids. I had a scale factor. In the first example, I multiplied by 2. In the second example, right here with the cylinder, I multiplied by 3. 2 was for the prism where I gave you numbers. 3 was this problem where I just did it abstractly. What effect did this have on the area? What effect did this have on the volume? Well, for the prism, when I multiplied by 2, the surface area was multiplied by 4, the volume was multiplied by 8. For the prism, the surface area was multiplied by 9, and the volume was multiplied by 27. Now, hopefully, you are familiar enough with these numbers that you can see what is happening here. The scale factor right here is 2, 4 is 2 squared, and the volume times 8, that's 2 cubed. Here I see 3. 3 squared is 9, 3 cubed is 27. So, this is the general idea we want to have. If I multiply my dimensions by a certain factor, the area will be multiplied by that factor squared, the volume will be multiplied by that factor cubed, which is fitting, again, if you think about the units, area is in square units, volume is in cubic units. Now, we don't want to just think about multiplying one particular dimension. This could be a fraction, or more generally, I could give it as a ratio. So, let's generalize this at this point. So, let's say I have a certain scale factor. Now, the scale factor, when I talk about this for similar solids or similar figures for that matter, scale factor always refers to the ratio of corresponding lengths. Now, when I say lengths, I could mean the length, width, or height of a prism. I could mean the ratio of two radii, or heights of cylinders, or even slant heights for cones and pyramids. The other thing, though, be aware, corresponding lengths would include perimeter or circumference. All right, so if the scale factor if I have two solids whose corresponding lengths are in the ratio of A to B, well, then the ratio of the corresponding areas will be A squared to B squared. The ratio of corresponding volumes, or just the overall volumes in general, is A cubed to B cubed. So what we're going to do is use this idea, and we have to keep this straight because this will be used for sure. We're going to use this idea to do some problem solving so that we can do this when I don't know any of the actual measures, or maybe I don't even tell you what type of solids they are. I just tell you I have two similar solids with a particular ratio between areas or between the volumes, or I give you the scale factor, or I say the ratio of the radii, or something like that. All right. A to B, A squared to B squared for areas, A cubed to B cubed for volumes. So let's take a look. Right here, each of these rows describes the ratios between two similar solids. I want to fill in the missing entries. So in the top row, I've given you the easiest one. The scale factor is 3 to 4. I want to know the ratio between corresponding areas and the ratio between the volumes. So if the scale factor is 3 to 4, again, this is A to B. The ratio of the areas will be A squared to B squared. I'm actually going to write this above the column. A to B, A squared, B squared, A cubed, B cubed. All right. So if this is 3 to 4, then here I will have 3 squared to 4 squared for the ratio of the areas. Now it's not going to be left that way. It will be rewritten as 9 to 16. For the ratio of the volumes, I will need 3 cubed to 4 cubed. 3 cubed, 3 times 3 times 3 is 27. 4 cubed is 64. All right. Now what if I don't give you the ratio between corresponding lengths? What if I don't give you the scale factor first? If I give you the ratio of areas, then I need to understand that right here, 4 to 49 is A squared to B squared. So what I'm going to ask myself is, okay, what numbers do I square to get these things? What do I square to get 4? What do I square to get 49? Well, that's not too bad. 4 is, of course, 2 squared. 49 is 7 squared. So once I have that information, I can go and figure out the scale factor. I can figure out the ratio of the volumes. The scale factor will just be 2 to 7. The ratio of the volumes will be 2 cubed to 7 cubed. 2 cubed is 8. 7 cubed is 343. All right. Last example. I have 125 to 216 is the ratio between the volumes of two similar solids. Now again, I remind myself that this is A cubed to B cubed. So you have a couple of options. If this is a ratio, these should be cubes or squares of, they should be perfect cubes is what I meant to say. So 125, 216, I could just guess and check until I figure out what those are cubes of. I could also use a graphing calculator to take the cube roots of these numbers. Either way, what I can see is for 125 and 216, this is actually 5 cubed and 6 cubed. So once I have that information, I'm always going to go right back to the scale factor. The idea is to use the scale factor to find the others. If I give you the volume, I'll go volume to scale factor and then go back to find the area. All right. The scale factor is 5 to 6. The ratio of the corresponding areas will be 5 squared to 6 squared, or 25 to 36. So you can see all the answers I have filled in here. Right? And now I have this filled out. Again, it's all about knowing these relationships, that the scale factor, the ratio between corresponding lengths is A to B, corresponding areas is A squared to B squared, corresponding volumes, or just the volumes overall, is A cubed to B cubed. So, knowing that, it's a matter of essentially just playing with the numbers to make this work. Now, let's take a look at this next example right here. The volumes of two spheres are in the ratio 64 to 343. If the diameter of the smaller sphere is 20 centimeters, what is the diameter of the larger sphere? All right, so when you're looking at this problem, it's telling you about volumes, it tells you they're in a ratio, so that's a clue that you're talking about this type of problem. You notice that it doesn't say that the figures are similar, but something that we should be able to think about and realize, all spheres are similar. Which should make sense because the only thing that really determines the shape of a sphere is the size of its radius, or for that matter, the size of its diameter. Similarly, all cubes would also be similar. All right, so the volumes are in the ratio of 64 to 343. The diameter of the smaller sphere is 20 centimeters. We want the diameter of the larger sphere. So first off, let's figure this out. The volumes are in the ratio of 64 to 343. Well, if this is volume, then I know that this is a cubed to b cubed because it's volume. So then it's a matter of saying, okay, well, what is the scale factor? What is a to b? Well, again, you can cube root these numbers. If you followed along with the last example, you should be able to pull out that 64 is 4 cubed, 343 is 7 cubed. And I'll write that over here for a little bit of clarity. 4 cubed is 64, and 343 is 7 cubed. I write that in bad order, sorry, but you got to know what those are cubes of. All right, so what it tells me is the diameter of the smaller sphere is 20 centimeters. We want the diameter of the larger sphere. So diameter would be a linear measure. Diameter is a length. Which means what I'm going to do is use the ratio of A to B. A over B will be the ratio of the two diameters. So 4 over 7 is equal to, going back to the problem, it says the diameter of the smaller sphere is 20 centimeters. We want the diameter of the larger sphere. So the smaller sphere, 20 centimeters. The larger sphere is unknown. You can put d or x. I put d for diameter. And what I want to do is solve this. Now you can solve this in a variety of ways. If you choose to do this by cross multiplication, you will have multiplying these two, 4 times d is equal to 7 times 20. 7 times 20 is 140. And then if I divide by 4, the diameter is then 35 centimeters. Okay? So be aware, this is how problem solving with these things will typically work. You will have to go from a cubed, b cubed, or a squared, b squared, down to ab. And then depending on what the question asks, you might need to use ab, you might need to go back up to whatever other dimension. I know that's sort of hard for you to understand with me just saying it, so let's actually look at an example. But again, understand this first. The volume is in the ratio a cubed to b cubed, so the scale factor is in the ratio of a to b. So that's what I use to find the missing diameter. All right. Two similar solids have surface areas of 75 square inches and 192 square inches. If the volume of the larger solid is 756 cubic inches, what is the volume of the smaller solid? So hopefully I didn't make an error punching these numbers in. I think we should be good. Let's go ahead and take a look. So, two similar solids have surface areas, and we want to know something about volume. All right, so areas are in a ratio of a squared to b squared. So a squared to b squared is 75 over 192. Now it's tempting to just square root these right off the bat, but you should probably recognize that 75 is not a perfect square. 192 is also not a perfect square, but that's probably not as obvious. So what are we going to do here? Well, the first thing you probably want to do is simplify this fraction. 75 and 192 are both divisible by 3. So if I divide a 3 out of both of these, what will I get? 75 divided by 3 is, of course, 25. 192 divided by 3 is... What is 192 divided by 3? Sorry, I'm having a blank here. Alright, sorry about that. I had to go grab a calculator to check my math. I'm glad I did because I realized I made an error. I wrote down the wrong number. So instead of 756, let's make this 768. Alright, 192 divided by 3 is 64. Alright, 25 and 64. If 25 and 64 are a squared and b squared, then I can figure out that a to b must be 5 to 8. Okay? Now, I am then asked about the volumes. So the volumes will be in the ratio of a cubed to b cubed. So 5 cubed, 8 cubed, these are 125 and 512. Alright, so you notice I changed this because I realized I had in fact made an error when I wrote this problem. But I've now got 125 and 512. So 125, 512. The volume of the larger solid is 768. The volume of the smaller solid is what we are trying to find. That is unknown. Okay, so you can put x, you can put v, what have you. Now, when you multiply this, you're going to get some fairly large numbers. 125 times 768 is equal to 512 times x. Now you can go ahead and multiply 125 by 768. And this gives you 96,000. But don't let that large number scare you, because what you're about to do is divide it by 512. And if you divide that by 512, what you get is a nice answer of 187.5. Alright, so 187.5 means the volume of the smaller solid. My full answer with units, 187.5 cubic inches is the volume of the smaller solid. Right? So, again, be careful. You might want to rewind this to think about it a little bit. But the areas were in the ratio of a squared to b squared. These were not perfect squares, so I went ahead and simplified the ratio, which told me since this is 25 over 64, the ratio of a to b must be the square roots of those two, 5 to 8. The volume is then the ratio of the cubes of those two numbers, 5 cubed, 8 cubed, 125, and 512. So I then set up my proportion, and I went ahead and solved. Big numbers, but everything worked out okay. I didn't get anything funky. 187.5 cubic inches is the volume of the smaller solid. Alright, so that shows you some examples of how you can use these similar solids, how it works in the context of problem solving. Now, one thing that I want to go back to, I mentioned this in the beginning, and I talk about it more in class. What if I don't actually create two similar solids? What if I change dimensions by different factors, or I don't change them all? And again, I wrote down not the right number, so I'm going to fix that real quick before you see it. So let's go ahead. Right here, I'm going to take a rectangular prism and multiply its its length and width by 4, while its height is multiplied by 3/2. And we want to know what effect this has on the volume. Alright, so, you can sketch a prism if you'd like. It's not really necessary. And what are we going to do? The length, the width, and the height are all changed. I don't have to change them all. In fact, sometimes I won't change them all. But if they are all changed, the length is multiplied by 4, the width is multiplied by 4, the height is multiplied by 3/2. So the question is, what effect will this have on the volume? Well, the volume of a prism is simple. Length times width times height. And now I'm going to substitute in these new dimensions. So my new length is 4 times the original length, my new width is 4 times the original width, and my height is, I wrote 3/2 W, pardon me. My new height is 3/2 the original height. Alright, so then what I'm going to do, 4 times 4 times 3/2. 4 times 4 is 16, times 3/2, well, half of 16 is 8, so times 3 is 24. So this is 24 length, width, height. Okay, so I have multiplied the volume by 24. Okay, so this is an example where I did not change them all by the same factor. I changed them by different factors, and you see that the volume has been multiplied by 24. Alright, so I want to go ahead and do one more example because that seems a little bit tricky now that I've done it. Alright, pardon. So, one more example. I had to find a blank sheet of paper. The radius of a cone is multiplied by 9. We want to know, how does this affect the volume? So we have a cone. Draw a cone. And what did I say? The radius is multiplied by 9. So I will replace the radius with 9. Well, when I'm finding the volume of a cone, the other thing it depends on, of course, is the height of the cone. I didn't say anything about the height, so the height remains unchanged. The volume of a cone is 1/3 pi r squared times the height. If I replace the radius with 9 times itself, the height stays the same. 9r squared is 81 r squared. So, we saw this sort of before when I did the example with the cylinder where I changed all of the dimensions and I was doing the surface area. I could multiply 1/3 times 81, but I don't really need to, and it doesn't really help me to do that. Looking up here and looking down here, I want to know how the volume has changed. Well, hopefully it's pretty obvious. What has changed? Multiplying the radius by 9 has introduced this factor of 81. So since I've introduced this factor of 81, I can say that the volume is multiplied by 81. I hope this has been helpful. Thank you.